Hi everybody, this is Ron Batum with Atlanta Functional Programming, and welcome to another episode of the Common Lisp Study Group. As all you know, Atlanta Functional Programming is a meetup that's dedicated to try and talk through and discuss functional programming as a dominant programming paradigm in large-scale software systems design. We encourage folks to give talks on functional programming and their use of it as their design and implementation patterns for their software systems in any language, whether it be Common Lisp, Haskell, F#, C#, or whatever. If you have a talk topic related to functional programming, please feel free to contact me. I'm Bugram on both Functional Programming Slack and the Lisp Discord server. And also, you could ping me and send me a personal message on our meetup page when you subscribe. Additionally, you could also contact Jed Taylor too as well. He's also available on several platforms in functional programming Slack, as well as I think you're on the Lisp Discord server as well. Today we're going to be discussing the final pieces of our overview of the cells dataflow programming library that we've been covering for the past couple of weeks. Today, specifically, we're going to be talking about the concepts of drifters, as well as how to handle cyclic dependencies inside cells. And finally, there's a concept in cells related to like neural networks called synapses that allows you to essentially define networks of cells where changes in a cell will only get propagated through the network, provided that a certain threshold is upheld. Once that threshold is passed, it will go ahead and trigger that network. And we'll discuss this later on, but let's get started. I thought I would begin with sort of giving the motivations behind drifters before we actually get into the syntax a little bit. So a common thing that a lot of folks do in defining their software systems, define some sort of counter, some sort of reduction, if you will, or aggregation of a particular value over time, so that they can keep track of how many certain records or how many certain data items have been processed. This is common, at least in data processing systems, when you need certain aggregations to provide some sort of summary to folks saying, hey, this is how much of the processing that's been done, this is how much is further, and so forth. One way of defining this is we could go ahead and define a, first let me go make sure that we load our definition. And furthermore, let's go ahead and change ourselves into this package. So one way of actually defining this is by defining a def model on, say, a counter that has the following slots. For example, you might have, say, let's call it items processed, if you will. And this one is obviously going to be, say, init formed to being a 0. Okay. Sorry, cells cin. Let's go ahead and make sure that our syntax is correct. Yeah. cin 0, and this is initialized to represent the number of processes that are available to this. Of course, you want to make sure that you have some sort of accessor to getting the items processed from the counter. And you may also want to, for example, to put a remaining items. Okay. And this represents or even we could say current items that we have yet to be processed. And this is going to keep track of just how many items we have in a particular list that we have yet to process. Okay. So in this example, and let's go ahead and do this and make this a yeah, go ahead and make this let's make this guy into a default cell. Let me just get the syntax here going correctly. We have this into cell nil because we don't want it monitors really. We don't want it to change. And you'll see why in a minute. This is going to be our, you know what, I take this back. This is going to be our nil cell. And this guy here is going to be our process in Excel. Okay. And the reason is in the initial thing that we've encountered, we want to be able to initialize a particular value for this element, but we don't want to necessarily go and trigger a change in the items processed. Okay, so we're gonna go ahead and do this manually. Okay. So what this does is this counter is going to then be used in the following way, and this is, we're going to call this non-drifter counter just to be more complete about it. Okay, so we have our thing here. Now, obviously, since we are not triggering this, this. Since we're not actually going to head and trigger the cellular network, we want to have some way of updating items process. Well, one way of doing this is remember, we have def observers available for us, right? We can actually go ahead and do def observers here, right? And we can go in and change on our current items, okay? And obviously, remember the syntax, right? Here, just to show you it, here we have our examples earlier on that we've encountered def observer on. It might be better to use this other one here. So we have our specialization on self, and this is going to take our non-drifter counter. Okay, and it's going to be the new value and the old value, whether the old value is bounded. Okay, we want kind of all the old, all the setup kind of in there, just because of the fact that right now we're not triggering. We may get the first initial trigger when the construction occurs to actually say that something's been bounded or not. Okay, and what we want to do is we want to use this old value here. Let me just go ahead and close this guy out. And when it's bounded, we will do the following. And actually, it might be better if we just do this as an if-else. And if it's bounded, what we'll do is we will set f items processed on self to being associated with essentially the addition of the new value, okay, the old value, actually, you know what, I take that back, we can actually do this even better. we'll first initialize it when it's bounded Got it. So what we have to do is if and old value p and we haven't initialized let's do it this way. So when we bounded it and we don't have it the first time, okay, what this code is going to do is it's going to first initialize our code, okay, and what this does is it will go ahead and set the items processed to be the first old value, okay. The reason is you want some sort of initial value associated with this particular thing, and right now we don't want we want the new value to be used as part of the aggregation later on. Okay, so what we'll do is we set the first time items process to being the old value. Now, every time we process something and we update current items, we could just simply say, you know what, this is going to be items process self is now going to be the plus of itself. And the new value. Now, I know I'm not, for folks who are watching here, I know I'm not using, like, say, width slots. I could certainly do width slots here too as well. But I'm showing kind of the code as to how the structure of this observer is going to be. Okay, so now we have our observer, we have our initial counter. So what we can do now is when we first initialize, let's do this here, on the REPL, we first create our parameter, our basic counter, call this ND counter, we make an instance of non-drifter counter. Okay. So now we have this, and if we look at current items, if we look at current items on the ND counter, this is initially set to 0. Okay. Additionally, if we have items processed on ND counter, you can see that this is also set to 0. And when we call current items on ND counter, and let's say that we set this to 3, you can see now that items process counter is set to 3. Okay, and it'll keep going through this. Okay, so when you're using this code, let's say that we have a function, right? Let's say that we call this try ND counter out, and we go ahead and let our ND counter be make instance counter. Okay, and let's say that we're processing lists of lists. Okay, so let's say that we have do list, okay, of L, and 1, 2, 3, 4, 5, 7, 8, 9. Okay, actually, let's say 6, 7, 8, 9. Okay, and before I do this, I'm going to go ahead and make this into a prog-n, so we can actually add one more piece of code in here, which is we're going to go ahead and format t and say what we're processing. Okay, and this is our new value. And after this, we could also say current total processed. Items processed itself. And I'll do some cleanup here for folks just so that so people can see how like some of the best practice to actually go leverage this. Like for example, here you could certainly use say with slots, okay, and you provide the slots that items processed, and you call the instance, which is self, and then we could just simply move these guys. Controls. Good. Now we could just simply do this. And this is more idiomatic for folks who are looking at this, just so that so this way now you don't have the items process, the accessor in all sorts of places. You access it kind of once. And what we do here is we could just go ahead and we could just simply iterate through. Let's say we're going through and doing this. In fact, this might be better. Let me do this better. This might be a little bit better to do. I'll go ahead and do this. Okay. Let's do it here. Processing. And actually, let's go ahead and make this into the current items that we're currently processing instead of what we did before. So now this ends up becoming here. Make it even more complicated, right? And length for folks who are just coming in from other languages is kind of like size. It will take in the sequence of the elements, and it will go ahead and convert them to the appropriate it'll just go ahead and find the size of the elements, and then it'll go ahead and return that accordingly. Think of it like size in C++, or length I think is also used in Java too as well. So what we're doing here is we now we're processing these items, and what we could do now here is we could just go ahead and say we're processing these items here. And for folks, this is a quick iteration format string inside. Common Lisp that allows you to iterate through without actually having to write out all that stuff. And we could just go ahead and say this. And we can also set F on current items on our MD counter. And let's set it to the current list that's being processed. And obviously this here, let's just make sure everything got compiled here. Current items in counter. And format T, say total processed. It's a items processed on MD Okay, so now let's do a quick cleanup here just before we can get started on the code, on what this code is actually doing. And we run it. Mainly, we'll do this. Start. Oops. Okay. So now bring this down. Oh, down with slots, items processed, items on ND counter. This items. We're missing one more thing. Control. Oops. Control C. Star. One second. Let's see where this guy is. Oops. There we go. Much better. So this now should compile and everything's good. All right. And before I forget, yeah, I have all that good. Okay. So when we run this, okay, what this code is doing is it's going to iterate through each of these lists because it's a list of lists. And what we're doing is we're grabbing the instance of the non-drifter counter and we're setting the current items and we're going to go ahead and process them one at a time. All right. Now when we run this here, you're going to see quickly that it's going to be a bug. 1 second. Oops. Sorry. Not counter. Apologies. Okay, so this looks wrong. I may have incorrectly set something up. Let's see here. Oh. Right. You want to use old value bound P and actually that's right. Let me see something here. So when it's first, otherwise, let us check something here. Let's check something. Old value outbound. Key items. Current actually, you don't even have to do that. You could just do old value at this point. Okay, let's see what happens here. I'm going to run this. Okay, so this here, and we've set, aha, so it's not actually calling our def observer in this case for some reason. Let's see here. Why is it not calling that? Oh, no, it's because it's not. Got it. Let's see here. Let me just do this one. Equals items process self 0. Let's see what happens. Aha. Okay, so old value is round, old value is new, but it's not actually set. Okay. 1 second here. Select items, drifter things. Okay, this should work, but for some reason it's saying that it's not bound. So we're going to do a little quick debugging here. Value. Let's see. Value. Sometimes you're going to have to go through this quick debugging when you go through some of these examples. So we have this. Okay, let's go and run it. Old value, new value. So the first time it gets constructed, of course it's going to be set to 0. But then it's not calling every time. That's the problem. Okay, I see. It is not calling because, let me see if I switch this over to doing this. Sometimes this happens when we're using width slots. Let me see if I can do that. There we go. All right. So the reason was there's an issue with cells. I forgot that in cells you can't use the cell network doesn't actually work well with width slots. So even though width slots will allow you to modify an existing list, it doesn't trigger the rest of the infrastructure. So I totally forgot about that. But so my apologies. But now we can actually go through this a little bit more and actually understand what's going on here. So the first time we construct this, obviously, and let me actually do this to make this a little bit cleaner. And let's try that. Okay. All right. So the first time we constructed this, as you saw here, everything is set to null. Okay? And because it's set to null, it's going to go ahead and skip it. And it's going to go into the essentially the else clause here. all right, if you will. And in the else clause, because this is nil, so this is kind of doing it a little bit unoptimized way, but it'll work anyway. It will say items process is 0, length of nil, just to let you know, is going to give you the correct value of, if you give a length of an empty list here, it's going to go ahead and give you the correct value of the empty list, which is nil. And you can't add, and both nil and the empty list will work here. So the first time it's going to go, and when it constructs it, it's going to set this to its initial value, all right, for the current running instance. But the next time it's going to go through, it's going to go and set the actual list of the current items being processed to this list here, 1, 2, and 3. And now it's processing that, and that will trigger this event to actually go in and sum up the current total that's being processed. So the first time we go through, we get 3. The second time we go through, it gets 5, and then so forth. As you can see here, there's quite a bit of code that we need in bookkeeping that we're kind of actually go through, and there's obviously places where you can create error here. One, you have to understand the fact that you are managing this cell here manually. Okay, this is a very important thing to understand. Okay, that cell, the fact that it's nil, remember we've talked about this in previous weeks. It is a cell that is registered as being a cell in a model with respect to the cells library, but it's not a cell in that it doesn't register with the actual change propagation system that cells provides, and as a result, any observers that are attached to existing cells that need to go and manually set that will have to accordingly do so. All right, and this is why we have this observer here. Obviously, this is such a common occurrence, though. Like, we have some sort of aggregation like this, where we have some sort of input cell or set of input cells or set of data items that need to trigger some sort of condition that keeps a running total, if you will, of what's currently being done, right? And that's kind of the motivation behind what a drifter is. A drifter cell is a type of rule cell that ultimately allows you to keep track of the running total. The body of the drifter cell essentially keeps an additional state that represents what's currently been aggregated. Okay, so what does this look like actually? So to create a drifter cell, first let's create a new model, and we'll call this drifter counter. Okay. And before we do that, let me go ahead and move this guy here. So this way we can have both of our, and what we'll do is we're going to label this as try counter now, and we're going to pass in the counter argument. Okay, so instead of this now being this, let's go ahead and kill this guy. Take that guy out, and we're going to use the same sort of names inside of our drifter counter, okay? Okay, so now we have a drifter counter, and what this drifter counter model is going to have is the same items processed with our accessor processed and our current items. Okay, and this one, of course, is going to be still our input cell, okay, into the cells network. That will start off as empty. Okay. So what does this second cell look like? This cell that previously was manually monitored, manually managed. Okay. The way you actually create a drifter cell that essentially implements all the machinery that we wrote earlier is you create an init form. Okay. you say that cells C dot dot dot, that represents a drifter cell. Okay, now you provide it an initial value. Okay, in this case, it is going to be 0. Okay, you can also technically create this as being an appending list if you wanted to, a dynamic list. If you're doing a list of items, and I can show you how we could simply change that later on. But for the sake of example, this is what we're currently doing. So now we have our drifter cell with an initial value of 0. Well, what's going to be the actual change? It's going to be actually nothing more than attaching to the length of, and hopefully I have the caret. No, I don't. Unfortunately, the caret syntax does not exist here, it looks like. Yeah, caret syntax is used for other things, but we can't use that for now. So what we'll do is we'll just say current items of cells self. Okay, and we've been doing this in other examples. If you see cell self, this essentially is the running instance of the cell. Okay, now let's go ahead and show how this might work. So we're going to have let's create our ND counter from earlier. And we're going to also create our actual drifter counter. We'll call it eCounter. Make instance eCounter. Okay. Let's go ahead and grab this and compile it. Okay. So initially, you have our ND counter and our drifter counter. Okay? And if we go and look into this initially, this counter has the following slots. All this is machinery that's part of the cell's infrastructure, but then we have the additional slots, current items and items processed, which is our 2 items that we just created, right? So now what we'll do is we're going to go ahead and pass try counter to the ND counter to try counter first, and you'll see that, as before, it's going to go ahead and generate the same kind of issues here that we did before, right? But if we do try counter on counter, notice the same aggregation is going to occur. 1 second, once I figure out what this is. Oh, sorry. He said counter, not try, drifter counter. If we pass in our drifter counter to this, you can see that it's the same processing as before. It's taking the items that have been presented to us, each of the subsequent lists, and it keeps track of this running total. And it does that all behind the scenes. If we actually go and look at this here, and we see what actually gets generated, you'll see that this particular thing here, this make C drifter instance, is actually generating the code that essentially registers a callback that behind the scenes will go ahead and make sure that the state is consistent. And that's followed by this rule here. Processing of these rules occur as part of the change propagation system. Drifters are very, very useful for aggregations, like I said. You can certainly use them additionally for for other use cases, but the construct that we provided, this C dot 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 syntax, this is very important because of what it for drifters, because it creates a drifter cell and it essentially initializes it to a particular initial values. Okay. Additionally, this dot 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 registers a callback so that every time any particular elements, any cells that are part of this that change, the appropriate callback gets called, and the state gets updated accordingly. And in this case, it'll be items processed will get updated with the current running value that we currently have. And you can see that this would actually also work if you were to say, in other cases, in terms of processing. But I'll let you work around some of those examples if you need to, like keep a running total. Well, not just a running total, keep track of what's currently been processed, like the contents of what's currently been processed. Then that will be a little bit of an exploration on folks' end. Any questions? All right. The next thing that we're going to be talking about is it's going to be related to kind of like cells in general. It is very possible to go ahead and create a network inside cells. As you can see, this is very simple and very straightforward to actually go in and use cells. That it's very, very possible to write cyclic code in cells. Okay. What do I mean by cyclic code? Okay. What I mean is you created a cell that essentially says, let's say that you have a cells model that has an A, and when A changes, you need to take some sort of action on a B. Okay, which in turn requires you to update A again. Okay, and so forth. So as you can see already, we've created a cycle here. This is a two node cycle that occurs. So A needs to, in this case, still has to run in order to keep the code and the system in a complete state. Okay. I'm not going to kind of illustrate this particularly just because of the fact that if we write this very, very carefully, you're going to end up getting some sort of like integrity check code. This code, if we end up seeing something like this, okay, and it's very easy to write it with, actually, you know what, let's just go ahead and write this out. So you may have like a cells model called a cycle, okay, and you have an A here that has an accessor. Let's call it cycle A. And the init form is the fact that it is an input cell. Okay, and both of these are going to be input cells here in this example. We have an accessor here. Cycle E, init form. So, oops, it's not in the format. Okay. And you have, let's say here, let's go ahead and make this. This is our simple model, and we create two observers. So the observer on the first one that will take in some sort of new value. Remember, you don't necessarily need to specialize this guy, but I do anyway, just to make things, a little bit more consistent. Say that this is going to be a cycle object, and of course, this one, def observer cycle A, you have new value, old value. It will generate all those guys for you. All right, so combine that in such a way. And here we could just go ahead and say set f cycle B to the new value that's being provided. Okay, and let's do this. So, okay, and let's go ahead and def. Looks like we have to provide the new value in this case. Let's go ahead and do this. Looks like SBCL is a little bit more, it's a little bit more stringent on that. instead of reading through what's actually generated. And then in this case, we have another cycle with the new value, and this guy is going to go in turn call cycle A. Okay. This clearly, anybody who looks at this would say that this is going to clearly be some sort of, this is a clear example of a cyclic model here, right? So now, if we define, say, a function, trycycle, okay, that takes, an instance of this guy, and we just simply put two simple examples. We're not going to, really call much on this, okay? We're going to see what happens very, very quickly when we do, in this example here, we should mention here, this is straight out of Stefano's cell docs, because this one is a particular one that we should discuss. This here, if we call it right, it's going to end up having some issues, right? So let's see what happens. A and that cycle A and cycle B N. Sorry, just need to take a little drink here. Now, what happens when we actually run this code? Okay, this is probably going to lock up my instance, but I'm going to try anyway just to show you. Interesting. This did not. That I did not expect. Let's see, something here must have. Let's see. Cycle A, I'm set changing. Right. So you might be thinking, oh, it seems to be working, but what's happening behind the scenes is this. Weird. What should be happening is for this code here should have created a cyclic dependency, because this is clearly a cyclic dependency. This should be triggering this, which would be triggering that, and vice versa. But for some reason, it doesn't seem to be doing what I expected it to. Let me see why. So this might depend on your common Lisp implementation. It looks like there might be some sort of check here that's preventing this from occurring, which is a little weird, but we will certainly look at that. And let's see here, cell C should be cell C. I'm wondering if they added this built into this library. Let's see. They add an integrity check here. Probably not. Okay. Let's try this again. So what's going to happen is instead of doing this, you can see that this is undefined behavior. First off, what happens is when we set this, this is depending upon the common Lisp implementation. Common Lisp implementation should be throwing an exception. I thought SBCL threw an exception when I tried this code yesterday, but it looks like I may have tried it accidentally on closure and it gave me a different result. But depending upon your Common Lisp implementation, the behavior of this particular code example is going to change. In this particular case, what happens is that the A accessor gets updated, but the B accessor doesn't. It doesn't get triggered accordingly. Obviously, that's wrong because of the fact that now you have left the cell network in an inconsistent state. There has to be some sort of way of actually handling this. One way of doing this is you need to go and add something called a cell integrity check. Okay, and this basically creates an atomic transaction that makes sure that each individual cell in a cellular network gets the appropriate change propagation list accordingly until both are at the level that they're attached. So it will only run the appropriate number of times to make sure that A and B are both synchronized, if you will. Okay. And the way you do this is you do the following. You first wrap this guy, okay, the set F, in each of the observers, okay, with a cells with integrity, okay? And we'll see what this guy does in a minute once we see the final result, okay? So you redefine cycle A, and you also have to redefine the other one too, so that, oops, sorry. And now, when we run trycycle, you're going to see. Hold on a second. See this. Let's see what happens. That doesn't seem right. Let me try and do a restart of my Lisp. But sometimes it might be that my Lisp is in an inconsistent state. This occasionally occurs when I'm playing around with cells. Okay. Let's change that. Trycycle. Interesting. It does not do what I expected to do. This looks like a bug, but I very well could be using it wrong. Okay, let me see here. Did I forget something here in this example? We have an accessor, Cycle A, cycle B. Let me just do one thing. I don't think this matters, but let's go ahead and update these guys. And let's make sure that this is being called. Let's use format. Format T. Cycle. Called. And let's go ahead and put this guy here. This and do that. All right. Let's see what happens when we call this. Interesting. Now that kind of worked because it synchronized it. Let's say that we had that earlier. Just to show you the illustration. So without the integrity check, let's do that. We just simply did this, cycle B, self, new value, Okay, this is what we were expecting. So without the integrity check, it looked like there was some sort of um, preemption that both the observers weren't getting properly registered in some sort of sequence, and one of them was being called and just ignored. But if we add this format T, basically it calls an asynchronous call behind the scenes to print something out before it actually triggers the next call. And this will allow us enough of a delay for the network to actually behave the way we expect it to. And you can see what's happening behind the scenes here. A calls B, B calls A. Now we've seen a cycle, and if we go and look at the cycle error, it basically tells you that nil is not of type stream. So it gives you some sort of weird type error depending upon which common check that you provide. Okay, but now if we do the other one, okay, we actually go and switch this back to what we had with integrity, and we go ahead and do this also with integrity. You can see when we run it, it's called twice. And mainly the main goal is behind the scenes is the integrity check basically checks to make sure that the two values that represent the cyclic dependencies are synchronized. And if they're synchronized, then it will go ahead and it will say, okay, although I need to continue calling this other one based on the rule, since these are both the same value, I can opt out of actually calling it. So it will run only those number of times where the synchronization, the values of both things representing the cyclic dependencies of each other are not the same. Because that's essentially what you're trying to model. You're trying to model, in this case, that both of these values have to be exactly the same, right? So when you're building anything that has those kinds of cyclic dependencies, you can certainly do so, but bear in mind that it might run a certain number of things, right? Another way of actually verifying that this can work is that so if the error actually occurred, we need to make sure that we need to also call cells reset to reset the network. And what this does, it'll reset all the running instances models. And then when we call trycycle now, this is going to be consistent. Okay, sometimes if you don't call cells reset multiple times, you might get weird results. So periodically when you're especially playing around with multiple cells networks in your application, go ahead and run cells in reset to actually accordingly update everything. I mean, to reset the state so that you can actually get the correct behavior every time. This now brings us to kind of this other concept in cells, okay? And kind of the last concept in cells. Cells allows you to create these kinds of networks where there are these changes that will, trigger particular actions to occur. And we've seen up until now that a lot of these networks that we've built more or less will run instantaneously and very eagerly. But sometimes there's a case where you may want a certain number of items to be processed, or a certain percentage to be processed, or some sort of event to occur that makes sure that a certain state is upheld before you actually go and trigger the change propagation mechanism and allow the network to go into a consistent state. What I mean is you may have a threshold that you may want to kind of like verify that if the amount goes above that threshold, then that triggers the actual network to actually go and update itself so that it goes into a consistent state. This is very similar to what neural networks do when they encounter things that upheld some sort of sigmoidal function, where you have some sort of threshold where the actual neuron is waiting until a certain amount of energy is is available before it triggers and fires off a signal to the rest of the neural network. And you'll see that in a lot of cases when you go and implement things like, say, backpropagation and other sort of AI techniques. All right. In GUIs, this can also occur because in a similar fashion, you may want particular parts of the UI to change, maybe color or what have you, once a certain percentage is downloaded, or if a certain amount of data is processed, or if you're writing a data processing system accordingly. Or you may be writing an alert monitoring system where, for example, if your resources are above a certain threshold, you may want to go in and trigger certain actions to make sure that, the job distribution is actually balanced. So this way, you are actually utilizing all of your resources accordingly instead of hogging a certain subset of them. In this case, cells is at your disposal because cells provides you a way of actually providing these kinds of thresholds in in a feature that they actually call a synapse, which is kind of named after the technique that I told you that happens in neural networks. How do we go and model this? Well, first I'm going to go ahead and this particular example, comes out of the Stefano documentation, which I thought was pretty neat that we can go through. This one you may want to actually go and review in your own free time. But the idea is that a synapse creates essentially a constraint propagation system, right? And with synapse, you essentially are controlling how and when a particular change should be propagated or not. An example of this is if you wanted a particular thing to occur at a certain amount after a certain amount of time, right? Let's say you're mimicking some sort of clock for like a batch processing system, okay? And in this case, you may want to define, let's call this some time, and in this network, we have something like the current time, which we will set later on with some sort of accessor. And this time could be just an integer, if you will, right? So, and let's say that the init form, because remember, we're not, init arg isn't enough here. You need to go and provide an init form with the registration of the cell. And we're going to go ahead and say that this cell is an input cell with an initial value of 0. All right. And now we may also want kind of a wait time with some sort of defined accessor. And we have a wait time of form. And again, this is an input cell too as well. Okay, so given this clock, okay, so given a representation of a clock, and let's go ahead and compile this. Okay, and oops, sorry. Compile this, and let's change some of this code here a little bit so that's a little cleaner. Okay, so now what we may want to do is we may want to add, kind of a condition that's going to represent the synapse here in this wait time. Okay, so what we'll do is we want to periodically check if after a certain wait time, what the current time of self is. Okay, and this is based on some sort of sensitivity. All right. So the way we would model this is we will have, let's say this slot. Again, this doesn't necessarily have to be an accessor. This could be just simply a reader in this case. But I'm using an accessor because you may want to go and define, explicitly set that. Although that's that case will certainly be will make your network kind of out of sync because those values don't necessarily make sense. But the main thing is this init form. Okay, so this is an init form. In order to define the actual synapse, we need to go and actually first define a condition. This is a type of ruled cell, so we're going to certainly use a ruled cell. Okay. Now, what is this ruled cell going to use? It's going to go and use something called the sensitivity. Okay. And this sensitivity, if we go and look up the sensitivity, cells sensitivity. This guy is a macro that behind the scenes will go ahead and essentially trigger after a certain amount of wait time. Okay, so what this is doing is essentially is causing a delay between the time elapsed and the current time, because the current time is going to current time and time elapsed will both represent the same value of the current time, but only after a certain amount of time is going to occur. So how do we model this? So we have this F sensitivity. We're going to say that it's going to be a synapse. Okay, we're going to call it syn. We're going to say that we're going to wait for a certain amount of time. Okay, and we want when that certain amount of time passes, go ahead and take the current time of the self and set it. Okay. So this is ultimately what we're doing here. Okay. So if we go and macro expand this, it's going to actually show you that it's going to call a function called F sensitivity that essentially waits a certain amount of time. This is your accessor that it's going to take a trigger on. This ID here, the synapse ID, basically is used to later on query the syn. What's returned is this named synapse object that holds, that is of type F sensitivity, and that's what's ultimately held inside the network, inside the ruled cell. All right. This is not a this is a type of lazy cell, but it is evaluated always. So it's think of the lazy ruled cells where we have this always. So anytime you access it, it will go ahead and update itself. At least this is kind of how I understood how the elapsed time works, based on the documentation that I've been reading. So anytime it's run, it's going to check the elapsed time. If the network is, if it's past a certain amount of time, this time elapse will get triggered. Okay. So let's go ahead and define a function that essentially calls this a certain number of times. Okay. So we're going to call this guy. Sorry. Nice and time. So what this is going to do is that first we're going to create a instance of our syn time structure with a wait time of input 2, right? So since this is an init arg, you want to make sure that you're passing in a cell wait time accordingly that follows the init form. Otherwise, you're going to hit a situation where when you're using this sort of syntax here, or you're calling make instance and you're passing in an argument to an init arg argument where the init arg is representing a slot that's actually a cell in the cell network. When you call this, and this includes even cells that aren't monitored, so that's cells that have the colon cell argument set to nil. If you do not provide some sort of syntax associated with it. Now, in the case of the unmonitored cells, there's a special case there that I'll mention briefly. But basically, for all cells that are registered inside the cell network inside using the def model, if you don't provide some sort of cell type, especially when it comes to input cells like this, you're going to get an exception thrown. And we'll see that in a minute. I'll show you that exception. We've seen it in previous episodes, but I'll show it here in a second. It's going to throw it saying that you're setting something that is of type cell, it's not going to trigger some sort of event from occurring from the rest of the system. All right. Once we have this wait time here, okay. Oops. Let's go up one more level. Now let's go ahead and call this 10 times format t. Let's go ahead and say we're incrementing one time. Then let's go ahead and increment our current time. Okay. Now let's say what is the time elapsed of this? Okay. And we'll do time elapsed of the current time. Simple example. When we run this, try some time, you'll see that for a certain period of time, time elapse is going to be the same value, right? They don't get synced. So here, time is 0, then we increment to 1. Time is now 2, incremented 1. Time is actually technically 3 in between here and here, but since we haven't actually hit the threshold of 2 seconds, it's not going to actually go and update itself. So it's going to be 4, 6, 8, 10, all right? You can use this for other kind of things, but this is a very easy way to actually go and set up a simple polling mechanism too. You can also use this in other scenarios. I'm sure you could think of many other ones. But the point is this sensitivity function, this sensitivity macro, essentially registers this small network and makes sure that this particular callback only occurs after a certain amount of time occurs, which is represented by wait time. Okay, and more importantly, if we were to try and do this, which can totally botch things up, what's going to happen is, as expected, we're going to get weird. That should not have happened. Let me see something here. Let's do this. Aha. Okay. That looks weird. That should not have occurred. They may have fixed something here. Let's see here. Let me do a cells reset just to make sure that I'm not tricking myself into cells reset. Okay. Interesting. It looks like you are able to recognize it, and it will go and change what it is. So you don't even need to do what we showed here. You could just simply go and change this to 2, 5, or whatever, and it will go and update it accordingly. It'll be a set F, essentially. The difference between, I think, actually, the difference between this and what I was showing you earlier is, that's right, the difference between what I showed you earlier and this, which is this, and let's try to show both the notations. Okay, and this, let's call this A try. Is a difference in machinery and what happens behind the scenes. Okay, in the first case, this will not trigger a change propagation event. That means it will not behind the scenes do a set F on the init form. It'll just simply replace what we did in the init form with the init arg. Okay. In the second case, though, what's going to happen is this is going to trigger essentially your observer framework to actually work accordingly, right? And we could see that actually. I think if we actually wrote def observer on wait time, self same time, new value, old value, down P, we can actually see new value, old value. Just simply do new, old value bound P. Okay. Oops, sorry. I have to go and put cells in front of it. There we go. So now, if we do this, and do this, we call this accordingly, and do try syn time, you'll see new value, old value times b. But if I do the other one, I just learned something today. It looks like it's doing the exact same behavior. I would have assumed that it will just do a simple set F and doesn't trigger the registration, but it looks like it's actually doing what is expected. Weird. Why is that the case? Maybe it's because, let me try something, one more thing here, which is to illustrate my understanding here. Let's do, no, that's not going to trigger a change event then. Right. This does not actually have to be, in this case, this could be just simply this. But if I do this, this is going to change what we had before. Let me see. We won't be able to use this second one, but we'll be able to use this one. Let's see what happens when we do that. And as expected, this is going to work because it's not going to trigger anything. Now, if we do this though, we're going to see that since this is no longer part of the cell network, we're going to get a condition cell saying that this is an anonymous cell. Okay? So, bottom line, this particular cell, if you use the init form syntax, it looks like, and I just learned through that, you can use either situation. You can use with init args at least. You can use this sort of notation or this, and it doesn't actually change anything in terms of the input cell registration. The input cell registration is completely different. So that's it that we're going to be covering today. I thank you guys for joining us on our adventure through the cells library. Actually, there's one more topic in my notes that I forgot that I was going to illustrate. Yeah, there's one more topic. Before we go, there's one more thing that I wanted to talk about with synapses. I'm just going to go ahead and cover that today. And that is specifically related to this here. When we talked about synapses earlier, synapses were attached to a particular ID, okay? And this ID is not just anything, randomly associated with it. What this is actually representing is a particular rule, and that is a lambda that has already been registered with the rest of the system that defines how the synapse is going to get triggered, how the change is actually going to get triggered. Okay, what the rule of threshold is actually going to do. All right. What that means is of course, then is you can actually go and define your own sorts of odd rules for actually defining different synapses, okay? So it doesn't have to just be, if you're just doing like something that's greater than the threshold that we have here, you could just use the :syn that's built into the library. But you could also certainly write a different one. So let's change this here and illustrate this one with a very quick additional example, which I'm going to call odd. And what this is going to do is, all this is going to do is let's call this syn, okay? And let's change this entire model. I'm going to go ahead and change this guy with the following. We'll have a number, okay, with the init form being that it's a cn0, and again, this is an example that is also in our good old Stefanos thing that we can cover, and then whether or not it is an odd number, okay? And this is going to be nothing more than a filter that is going to be updated the following way. It is a rule that takes in a synapse, which we'll call syn. All right, this will obviously take in, remember earlier when we look at the rule, this takes in arguments. Whether or not we use those arguments later on, that's entirely up to us. In this case, what we're going to do is we're just going to simply trigger the rule only when if the number that was passed in to self was odd. If it is, then go ahead and pass the values of the self and propagate. Okay. Otherwise, we'll do values don't propagate anything. Okay? That's all this is doing. Okay? So let's go ahead and define an observer now. I don't need this anymore. On odd number, self odd sin, and what this is going to do is nothing more. It's anytime new value, old value, p, anytime we are bounded, we're going to go ahead and say that we propagated the change, right? All right. So now, what we'll do is we're just going to create a simple example here called defun odd sin test, which basically takes an instance of our odd sin guy, and what we'll do is do list, and let's say that n is taking in the list 1, 2, 4, 5, 7, 11, just some random numbers here, 13, 15, 16. No, this is kind of in ascending order. We can even be out of order, so like 16, 15, this kind of thing. Some list of numbers. And what we'll do is we're just going to set, just going to set our instance format to setting num to a set f and what we're going to do is now check odd number anytime it gets created, okay? And if the rule is written correctly, what this is going to do is it's only going to trigger anytime it sees odd numbers, so 5, 7, 11, 13, and 15, all right? So let's go ahead and run this guy, odd sin test, and we could see that odd numbers nil, it's nil, it's going to keep on going nil. So that means that our rule is incorrect. So let's go and check this guy out. If num sells self, it should actually go in and propagate. Okay, so this here so let's see if this works. Yeah, there we go. So 1 got propagated, odd number is now 1, 2 is set, 1 is still there, 4 is there, it saw 5, now it propagated, odd number is now 5, and you can see accordingly that anytime an odd number is set up, you can actually go ahead and move this out. The main thing to note is cells allows you to define these kinds of triggering rules with the with synapse syntax, and allows you to set up your own kind of like very complex formulas on how changes can be propagated. This is very similar to spreadsheet programming because of the fact that with synapses now, you now can do essentially what spreadsheets allow you to do, which is, do aggregations of various forms and so forth, and write very complex formulas whenever something gets triggered, and you can propagate that, accordingly based on certain thresholds and certain objects. So that's all I have for today. My apologies, I didn't realize that my notes was a little bit convoluted when I was writing this up. So that surprise feature there, I hope you guys get a kick out of it. Let me know if you guys have any questions. Otherwise, I will. This is the end of our overview of the cells library. I encourage you guys to go and look at it. Again, it is available on Quick Lisp. Play around with it, try it out, see what kind of like applications you could build up on. In fact, as part of the completion of our cells things, next week what we're going to be doing is that we're going to be writing a very basic application. It's going to be a live coding session essentially that will illustrate a lot of what we've discovered, just kind of like to complete this and wrap it with the bow. But I will discuss those details when we reconvene next week. So until then, thank you for joining. See ya.